affected. On Wednesday, most of the discussion was about, let me get to get some light here down. Yeah. On Wednesday, it was mostly about the phenomena, what's going on during corrosion, which, remember after the class talking about a few simple things, like what do you normally do if you want to protect against corrosion? And I think that the most common way is to try to isolate from the electrolyte. So you put a form of coating. It's the most common way if you need to do so. And the idea, again, is you always have an electrical pad. If you have a metal, it's conductive. So if you're going to use try to prevent the movement of the electrons, it only works if you have a galvanic couple, and that's the only thing that you're trying to avoid. So we're trying to avoid to have the reaction with the environment, typically. And that reaction is essentially to ionize the metal, and then you have a corresponding reduction reaction on the surface. So you have your anode in red here, and you have your cathode in green. And what happens at the cathode, as I said, depends a little bit on the environment. What happens on the anode also varies if you're getting 2 levels of oxidation of the iron or 3 levels of oxidation, whether you form an hydrate or you form a more compact compound. And it will vary with temperature, but the basic idea is the same, that even though you start with just one material, it will form these anodes and cathodes on its own surface. If you remember, I mentioned that the corrosion rate is going to vary. So here you have an underground storage tank that was not protected. It was the domestic installation. Consider a domestic installation, even though the tank is way bigger than what you normally have in your yard. What happened here, and I mentioned about water table to you guys. So the bottom of the tank, which you see on the right-hand side, has holes through it. And the top of it was pretty much the original wall thickness. So it's just an example. When I was saying underground, you can have a lot of variation. Well, that's the best example of that. Now, I will say that not all of the corrosion was external corrosion. There was a component of internal corrosion visible as well. But what was difficult to know, and it's often the case with these types of tanks, is if they sit in clay, essentially you have a little bit of a holding of the oil and gas. It was a gasoline tank. And from the time you perforate, it's not clear that that's when people realize they have a problem. And that's why we try to get as many of these out of the ground, because sometimes you can have a very small leak with the soil just essentially sealing the holes. So when we see the corrosion on the inside, some of it can just be moisture from the ground penetrating back into the tank and causing that corrosion. So there's just a lot going on. And I mean, for us in this class, the idea with control is if we put sacrificial anodes, so for this tank, it really means, and that's something it's a good time now to discuss. If I put a sacrificial anode around this tank, so I got the tank, and say I put magnesium. So I got a block of magnesium here. I just connect the two together. So this becomes my anode, and this becomes my cathode. So what's going to happen is on this side, I'm going to have the generation of the hydrogen or recombination of water. And over here is really where I'm forming the ionic magnesium. And you can use zinc, and you can decide to have many of those. And this is just the electrical connection here. Make sure it's all tied in together. That's really all there is to it. You need the soy to be communicating the ions. So if you have a very dry environment, like a sandy environment, this is very difficult to make. You have to put the anodes closer because you have less ionic conductivity in the soil. Yes?
Would you use one anode for this whole tank, or would you put several? And how big would they be?
Okay.
Do you have to go check and see if it's like disappeared?
Yeah. So the checking portion is, of course, is yes, and that's one of the limitations with these systems. Typically, you'll check every 2 to 5 years. It has to be part of the building plan that you're going to go and figure out what the situation is. As to how many, for a tank like this, I would probably put one on each side and be okay with it, and I'd put it maybe 5 or 10 feet away. I've not seen too many exact design for these small tanks because a lot of times it's not done. But on big piping systems, there's a project I was working on in a prison. They just had the whole heating system for all the buildings going through the underground and going to the different buildings, and they were using this anode protection, and they were putting it about every 25 feet or so along the line. And actually, now we talk about this. Their system was very, very simple. Let's go to that. Bunch of bond wires connecting to different sections of the pipes that you connect over here to different anodes in the ground. And what happens, say, 5 years down the road is you just go and open that little cover and you can test for the potential of the anode, and it's going to tell you whether you consumed it or not. And you can check also for the resistivity between the anode and the tank. So a lot of that testing, you don't have to go back and go underground. You really want to have an access point to do that. Yes? It's the ion conduction. So because otherwise you're going to build up. If you build up too much magnesium ions there, then it won't get anywhere. So you need that magnesium to diffuse in the environment surrounding it, and you also need over here to just get the hydrogen to go. So, and this is not really a problem. So what becomes the problem is here. And what you try to do lots of times is not to have this big chunk, but it's surfaces actually that you want to be active. Good question. Yes?
What is the typical material for the induction mount?
Over here, these were copper wires. Yeah, insulated copper wires. I mean, to some extent, the structure itself is conductive enough because we're not talking about high current. So I would say any metal would do, but something that's not going to corrode on the small diameters. I mean, copper seems, they had spools and spools of it on sites that I've been seeing. So, yes?
Can you also create a potential with have a power source and then just keep making it so your anode doesn't go away?
Exactly. So that's a system with a rectifier where instead of, you still need an anode underground and you try to use a more permanent anode, carbon for example, and what happens is it's over here that you set the potential difference between the two. So it becomes the same. You just put in line the rectifier. It's used for most pipelines, oil and gas pipelines. And again, you can go back and try to make sure nothing is going on with your sacrificial portion by testing. The issue with those, of course, is years and years down the road, is the rectifier being checked. Because if you run out of power on your rectifier, then all of a sudden you're going back to regular corrosion. Yes?
How about vertical placement of this anode?
Yes.
Obviously, you're talking about different stratification of water.
You would want to try to have it about the same height because of the water table effect and all of this. So if I have the application and I'm putting it on top here, and it's very dry, it's not really going to conduct ions with the structure. So all the system I've seen is in the same operation, you essentially have to dig wider, and that's where you put your sacrificial materials. Yes. Yes.
How do you decide how far to put it from the tank?
If you are a corrosion engineer, you have to go and test the soil resistivity, and you have also other testing for how corrosive it is, and that's how you size your system. But the bulk numbers I gave you, like 10 feet, is a lot of times they do the soil test, but they don't necessarily change so much the layout because they know the soil is going to change, so they try to be a little conservative here in the numbers that they're going to put in. If you try to do this in concrete, for example, it's a lot more of a problem because now we're talking about a pretty solid material. So all our ionic conductivity is really reduced. So you end up having to put it about a foot away or less than a foot away. So it becomes very difficult, especially if you're doing it after the fact. So if you have a concrete slab that has reinforcing in it, and you say, oh my God, there's so much chloride that penetrated into the structure, now I want to protect it. You have to drill a bunch of holes and put these anodes closely packed and connect them back to the steel. It's a very expensive process, yet I've seen it done. If you don't want to afford replacing the whole system and you want to stop the corrosion, that's the way to do it. Yes?
Did you say you're producing hydrogen at the campus?
You can. There are three reactions, and it depends on pH and your potential. So a very acidic environment is what leads you to a higher risk of forming the hydrogen here.
What were the others?
You just for a recombination of water, and the third one I forgot. The one we worry about is producing atomic hydrogen. And some of these also depend on, when I mentioned potential, so it depends if you're making iron 2 ions or iron 3 ions. You guys asked a lot of questions about this one today. It's good. All right, so let's go back where we were.
Sorry, last one.
Yep.
Just because access is so difficult, is there a reason that you don't just actually just charge or put a potential on the different, on the container itself?
If you put the potential here,
It's like an electrical connection from the surface.
yeah, you're not really, so you want to ground it essentially. You're thinking about grounding it and just putting it on a higher potential. There's something that's missing with this. First of all, it's going to be, if you ground it and you're effective in grounding it, it's hard to get that high potential because you need a couple volts at that point. If all you're going to do is really passivate it, and at a couple volt into the ground, you're going to have to supply a lot of current too. So you're talking about polarizing the system essentially, and I've not seen it done. Yeah, and there may be other, more fundamental reasons in terms of even creating that condition. Because when you can put a rectifier with, say, 5 volt, but that's not what you actually generate locally with the pipe. And there are also a lot of regulation if you're going to do this, and we're talking about public utilities. If you're protecting, say, the gas line with this system, then the water people would be up against you saying, I don't want the soil potential to vary dramatically, because then you start having stray current into the ground, and that will cause more corrosion than the other systems. So you really try to, localize the effect that you're creating. It's a problem with utilities, because under the same road you're going to have different types of pipes, and if you protect one, it typically has some consequences, detrimental consequences on the others. Now all these systems are subject to these stray current. If you're close to a power line, you can have some polarization that you wouldn't have in any other situation. So when you're crossing a power line with a pipeline, you have to worry about that. It's a big deal, unfortunately. All right, so the other topic that we just brushed on was the galvanic corrosion. So it's essentially the opposite of doing this system, where you get an acceleration of the corrosion because you're connecting two different metals here. It's not the same metal anymore. Same way as with the magnesium here. It happens on the Liberty Tower. And the reason is there's a combination of copper and wrought iron. When you see wrought iron, it's essentially before we started making steel. So it's not cast iron, but it is essentially a steel, but with a lot of inclusions, and it doesn't really have carbon as a strengthening factor. So it's a very low strength steel, if you will, and it's very laminar the way it's made. It was used in the U.S. in the 1800 all the way almost to 1900 before we started really making steel. Again, the advantage is it does have the ductility, but it's subjected to laminar tearing and all sorts of things. It's the primary structure here, and to the extent that you have moisture penetration or water between the primary structure and these clamps here that are attaching to the facing of the Liberty Tower, is where you're going to have your galvanic corrosion. So the copper naturally wants to corrode, so you see the green on the outside. So it does consume a certain current. The trouble is that it's not its own surface that has the anodic reaction, is the iron next to it. One situation of dissimilar metals that you don't have to worry too much about galvanic corrosion in general is between aluminum and steel. So aluminum and steel would be a little bit like copper is to iron. So the iron doesn't get corroded, the aluminum does, but the only advantage is if the aluminum is passive, it will be able to resist the galvanic couple. Now, there's a lot of things in terms of galvanic corrosion that have to do with differential sizes. So the biggest issue here, if you have the big copper structure, then you have the little clamps and you have the armature is right at that interface. Those rivets that are really making the connection, they're very small. So if it was all connected and bonded through the whole length, you wouldn't have a localized effect, but it's the proximity that makes things more terrible. So when you're thinking about a fastener going into an assembly, that's the component that needs to be the strongest. So lots of times we will use stainless steel if we have dissimilar material for bolts or rivets, just because we want to make sure that this smaller component doesn't consume a lot of the galvanic reaction. Yes?
So I'm still a little bit confused how the earlier chart that shows you the active potential,
Oh, yeah.
how that relates
Yeah.
to this.
Okay, so the galvanic series, I put it in because it's what typically you see, right, in a galvanic corrosion class, but we don't want to emphasize all the intricacy. So the story is, this is done in salt water where you put the two metals together and you see what potential is generated between the two, how much they interact with each other. It's like if you're trying to design a battery, you go through this and you say, oh, this is a great battery type of situation. The practical aspect of it, the reason I've put some arrows is you can see a little bit aluminum, very reactive with all the other material. When you talk about regular iron, it's kind of in the middle of the road, and then you have the copper and the stainless steel that are more resistant if they are in the passive state. So stainless steel here, if on the surface somehow you lost the passivity, then it becomes very close to a regular carbon steel, and that will happen sometime underground, and you don't know exactly why. Yes?
So if we're trying to predict the behavior, what happens in the Liberty, Statue of Liberty, so we can look at the copper.
We look at the copper and the iron steel here, and we see that the copper is further to the right, and therefore it's going to be passive, and the active material, the one that's going to turn into an ionic zone, is the iron. So we're lucky for that with the tower, because at least we don't lose the face of it. It's just locally where these ties are connected to the armature is where the corrosion localizes.
And why is that?
Why it's near? Because we're talking about moisture, so if it was all in water, then you have the whole armature reacting with the facing. But because it's just dripping water, it's only within like half an inch is kind of what we think about when we think about just atmospheric condition.
Oh, so it's local conduction.
Through the electrolyte, yeah, through the water. Yes?
Random question. If graphite is so noble, why isn't everything coming graphite?
Why you're not doing what? I'm sorry?
So, graphite on the scale of Axis Noble seems to be the best out of every one of these.
Yep.
So, why is it not that everything when put in the ground is covered in a small layer of carbon? Or am I completely interpreting this wrong?
When you put it into the ground,
Or why is graphite used on a regular basis to?
no, it's just listed there like platinum is. Yeah.
Are there costing methods where you can get a single layer of graphite on something like that aren't expensive?
Boy, I don't know. I think graphite is fairly soft. I would worry about it as being my protective layer. That'd be we use chrome, right? You don't need to go that crazy, and we know what the issues are even with chrome, which is very ductile. Even though it's very ductile, you can have just a little area where the electrolyte's going to penetrate, and then you have pitting. One advantage with chrome, and if you remember, we talked a little bit about plastic plumbing, and when you put a organic coating on steel, what you essentially setting the clock for how much time it's going to take for the moisture to penetrate all the way to the steel, because moisture and oxygen will penetrate through an organic coating. When you go to a metal like chrome, you almost eliminate that diffusion, but it's still typically not a perfect surface, and that's why you end up still with pitting corrosion. All right, so the galvanic corrosion, there are ways around it. If you think about it generally, relative size is very important, and then of course the potential and what are the characteristics of the most reacting material. When it's aluminum, you're thinking, well, maybe I'll be okay because it's self-protected. If it's iron or steel, then that's where you get the highest risk of changing. Let's go to copper just a little bit, because I think it's good for you guys to be exposed. This is coming of a potable water system, the hot water system in a big building. And you can see the little holes on this image. So the whole pipe looks great. You see the wall thickness. And then the little hole that we see are a little bigger on the inside. So that's the inside diameter in a cross section. And then you have a little bit of a hole on the outside. Now, of course, the question becomes, why did the corrosion localize just at one location? The first reason, if you remember, copper has a protective surface oxide, similarly to aluminum, but it's not very stable. So what happens with a copper pipe is, depending on the flow in the pipe, you can lose your protective layer. If you have too much flow, you eroding away that very thin protective layer, and then you start having regular unprotected corrosion. If you have a particle in your system, any debris from the burner or anything like it, that you create a local condition, and that's what can create, if you remember the crevice corrosion system, you have a different environment under the deposit than on the side of it. So you start that reaction and it will continue. And that's why after the fact you see these holes. Now, what was interesting that I have seen on a number of these systems is if you look at the outside of the pipe, it's the copper pipe up there, and it still holds water without dripping. So in the process of the water getting through the hole, when it gets to the outside, it's high temperature, and all the deposits in the water will just solidify and it can clog the hole. So it's not necessarily the most safe system, but I've seen it work in a number of systems. And then eventually you get too much of it, and it will leak, or somebody will, if you're at a location where there's thermal expansion and movement of the pipe, you can't really build up on the outside like here, and then you get a leak at those locations. So I think it's a scary example of practical crevice corrosion. The question of the environment, using the environment as a way to control the corrosion is possible if you have a closed loop system. So if I have recirculation of water in a building, for example, I can say I'm going to put additives to that water so I'll resist the formation of corrosion on the inside of the pipe. It works sometimes, sometimes it doesn't work. So what you see here are called tubercle, and they're not unusual tubercle. It's not tuberculosis, but tubercle. They will form, and they're not necessarily all contain just the iron oxide. It's a combination of iron oxide and deposits from the water. So what happens here is, depending on your flow condition, you can start forming a little small piece of this. And if you do, you encapsulate a certain portion of the steel, and now you have that crevice corrosion taking place. You're setting up a very different environment on the inside than you have on the outside. And the story is with inhibitors, the only thing you can do is try to prevent this from starting. Because once it started, there's not much of an effect of what you put in the water surrounding it. You already encapsulated your reaction, it will continue. So it's a big issue with plumbing systems where, you think you have it right, somebody comes with an initial load of water and inhibitors, it really comes with a truck, they control the concentration and everything, and then the system starts getting used, and if you don't make up for your loss of inhibitor over time, eventually you're faced with a situation, you pretty much have to replace the piping, unfortunately. So it's used, inhibitors are used more for industrial processes really than kind of regular building plumbing, but they will be used in plumbing systems, HVAC system quite a bit. I have that example here. This is the copper pipe, and you probably can see on the image, if you look at that bend here, right here, it's a completely different project, but you can see it's pretty thin wall, even though it's not polished, but it's much thinner than on the inside of the curve. So that's a situation where the copper pipe was not being protected, passivated, because of the local flow of the circulating fluid. So plumbing for heating systems can give you a lot more trouble in a building, especially if you have an open loop. So these systems that have problem typically are going to a well for a thermal cooling cycle, or they're going to an open tower for the same reason. So it's just more difficult. Controlling it, we talked about organic coatings already. I think you can tell there are limitations. And the main limitations is, just like I said, it's thinking about the time it's going to take for moisture to get to the interface between your coating and the steel in this case. So if you're using a hard epoxy and you manage to bond it, you can get up to 20 years. It's possible to get to 20 years, but if you're working on that barrier, and if it's completely submerged, like a vessel going across the ocean, it may not be 20 years. Maybe 10, 15 years is the limit for all that diffusion to take place and then starting the reaction on the interface. But I'm just trying to give you some sense of the options. It's possible, but you have to think about what kind of barrier am I creating. And the problem with a very tight barrier, if I put a hard epoxy layer, I need to make sure there's no entrapped moisture, because that can't go back either. So it's a two-way street. If you seal it, it's okay as long as you know exactly your environment. We'll go back to organic coatings because they're pretty relevant to a lot of what's happening. What's very common with the organic coating is to have a number of coats. And the idea there is to create that adhesion. So if you're looking here, you have the steel, you have a primer, and you have your top coat. And then the top layer is just a mounting material. But the idea there is you need adhesion. So you need kind of a sponge effect, something that will just absorb whatever is in there to begin with, and then you put your hard layer on the outside to make sure you don't get anything to penetrate on the inside. Yes?
What's the function of the primer?
The primer is mostly there as a bond, because your surface always has moisture, so you need to wet with that surface and capture that moisture so it actually absorb anything that's existing. That's really its main function. And then that material will adhere better with your hard coating that you put on the outside that's there as a barrier so nothing else comes back in. Yes?
How do you put it on? Do you like paint it or spray it?
There's all sorts of ways. So the epoxy is a two-part system, and it's got to be applied pretty quickly. And you can still mix it and apply it with a brush. It's still done. An advantage of a brush really is you're really mixing the surface. When you project, if you use a spraying method, you're more likely to create some voids between the two than if you really brush it. One way that I've seen kind of the best jobs done is you spray the stuff on and then you brush it to make sure that it's all bonded, and then you move on essentially to the next area. Now, maintaining the thicknesses there sometimes would be very important, because with your epoxy, if you put too much, there's no way it's going to stay adhere. You have too much of a mismatch when it's under stress. So that's a situation. Sometimes you just spray it with a very controlled technique, so you always have the same amount everywhere. It's very hard to just rely on the protective coating. If you have a critical application, you say in that corner, because that's what I was showing on the image, there's a corner here. So there's metal going this way, and then there's metal going this way. There's a weld. Over time, this is all going to expand and contract. We're in a tunnel here, and keeping these two materials bonded together is a big challenge. So what we end up doing a lot of times is we galvanize the steel. It gives us, a much greater life, and I don't want to get through all the details of galvanizing, but you see the different kinds here. So the hot dip galvanizing, I have some images for you, is really you take the steel. It can be rusty, right? When you make an assembly in a shop, it's very hard to all have very clean steel. So you take the steel, you put it in a bath to clean it with an acid, and then you literally dip it in liquid zinc. And you have to be careful what that temperature of the zinc is to not create trouble for the steel. But if you control your temperature, you dip it for a certain amount of time, you make a relatively thick casting of zinc on the surface. And the way you see those, the way you can confirm that it's hot dip galvanized when you see the individual grains, the big grains on the surface. So if we look here, a Stata Center, or even if you just a light fixture post outside, a lot of times it has been hot dip galvanized. And you're talking with hot dip galvanizing, you're talking about 2 mils thickness is typical. You can go to 5, so I'm just going to put a range. But it's fairly thick. So this becomes 2 mils is 1/20 of a millimeter. So it starts at 200 micrometers going up to 500. Yeah, I think. No, I'm screwing up here. Anyway, these numbers I know, and then you have to translate it back. The idea here is have enough so you can last the useful life. So what's the useful life of a typical structure? Well, a lot of people will say different things, but if you put your minimum at 50 years, it's not atypical. So say we have 50 years for a bridge, that coating will resist it. And how I know that is people have done studies of how much zinc you lose over time for different atmospheric conditions. And it is a lot less than it is for the steel. And if you put your hot dip galvanizing, on the whole surface, you don't consume a whole lot of it to protect the steel. It's a very, very minimal. And that's why a lot of times for car body panel, you're actually going to much thinner layer that you can generate. Either if the car body panel, they still drop it in liquid zinc, but for a very short period of time, and then they clean it up, and they do a post treatment to create more adhesion with the surface, to roughen that surface, because one of the biggest issue of galvanizing is adhesion of coating. So if you galvanize something, especially the hot dip galvanizing, it's very hard after that to put just a decorative coating on it. That's why a lot of times we end up just with seeing the galvanizing. And there are a couple of reasons for that. One of them is after galvanizing, for quite some times you're going to have a little bit of entrapped gas coming out of the zinc, and that itself will debond any coating that you put on it. The other aspect with the galvanizing, you see the grain, so it's a very, very flat surface, and therefore it doesn't allow for much mechanical interlocking. There's a shop here on the North Shore that Dulcan, and they do a lot of galvanizing for large structures, anything from bridge tunnels, large building structures. What they end up doing is after galvanizing, they will grind the whole surface. And what that does, the main thing is create these ridges for mechanical interlocking, but it's also deforming the zinc layer to try to get as much gas out of it very quickly. And they will guarantee their coating systems for 30 years. And the main reason they can do it is even if you have a little bit of penetration of moisture into the system, it doesn't create that big reaction of corrosion of the steel because the zinc is there. So you win both ways. In areas where it's protected with the paint, the paint doesn't come off because you have it doesn't come off because you're protected. You don't have a reaction at that interface. And if you look at the very surface of the steel and you scratch it, you expose the steel itself, then we're back with this system here, and that's how you protect it at that point. So it's a good way to do things, but it's more expensive, of course, than just using structural steel and applying the coating on site. So that has to be all done in the shop. Yes?
I have a question. So what sorts of corrosion protection mechanisms work best for I guess structures that undergo a lot of cyclical loading? Or I'm thinking like the turbine of a ship, for example.
Yep.
Would it like shear? Would you have to be worried about the shear surface or anything like that for coating?
If you have cyclic loading, and that's the next topic we're going to cover, like turbine components, you do need to worry about that mechanical compatibility, which is what you're referring. If you're going to have high loads,
Yeah.
you're thinking about the galvanizing not holding up, right?
Yeah.
Yeah, it's true. It won't. You can actually create cracks through it, and they're going to continue through the base metal. So for higher load application, you're starting to think about more expensive, and these can be metallic coatings, and you can spray them, and we'll cover that. Okay, so just a few more words about the sheet galvanizing. The reason I'm mentioning is this is, if you say to someone, I want my steel to be galvanized, you don't know, just the word galvanizing doesn't tell you which one of these you're getting. So be very mindful of that. If you want high protection, high thicknesses, you talk about a hot dip galvanizing, and you may have to specify thicknesses. There are ASTM standards that say, I want 5 mils thickness for this pipe, and that's great. If you all you want is kind of a minimal atmospheric resistance, then the thinner layer of zinc could be okay, except when you start consuming it. So here we have a hole in the galvanizing. This is the perfect situation where we want to use our sacrificial power to protect those surfaces that are exposed. But what you can see over here, the hole is approximately here. We couldn't show it all on that image. But from the hole you have on the surface, you've lost all your galvanizing over, you can lose it up to about an 1/8 to a 1/4 inch, depending on the condition. And then you see it here. But the problem is when you're far away from the hole, you're not protecting it anymore. So there's a certain limit distance where you can use the zinc because of the moisture drops. You can think of it as a drip of water. As long as you can cover that same area, you'll protect it. But if it's not in the same area anymore, then you don't have the zinc as part of your environment. If the zinc is not part of the environment, then you're back to corrosion of steel.
Sorry, I'm not sure I follow you about
Yep.
physical proximity.
So we drill a hole through our zinc layer, through a plate. So that starts here. And then over time, I'm consuming the zinc that was near the hole over here. And then what we're showing on the image is just this portion. Where it's a rapid drop. But what I was saying is if I'm thinking about a drop of water, so this is my hole, this is the surface that's completely unprotected, and now all of this is unprotected too. And this is becoming too far to protect what is where the hole is. So I'm done with using the sacrificial protection power, and now I'm going to lose thickness. If we had this hot dip galvanizing, we'll still be fine, because we have just a whole lot more material, about 8 times more material near the hole to protect it. Good. All right, let's see. So the hot dip galvanizing, again, is you clean the steel and you drop it. There's a lot of ins and out in terms of if you want to protect the inside of a tubular structure, which is very typical, you need to have access holes into it so the liquid can penetrate and get out on the other end. It's one of the biggest issues because you don't want to have too much zinc on the inside. If you're making a tubular structure and you have a lot of zinc on the inside, it can affect your mechanical properties. You can start cracking that zinc, and then it gets to the primary structure. So that's a big issue. Yeah, well, we've covered what I wanted to tell you about the steel. And I will say a few words about stainless for the reason that it does corrode. I'll pass these around. This is good quality stainless steel. It's austenitic 316 stainless, and it was an installation by the water. It's the same steel that's used for the Boston Aquarium. What happened to it, and this was not even exactly by the sea. So the issue with stainless steel a lot of times is with chlorides. So chlorides will attack the little protective film on the surface, and then when it started, you have that corrosion continuing. So you can see a little bit of these, but this was cleaned the best way we could. And this was clean, and does it have the coating on it? No, not yet. One way that to resolve the issue on this job, a few jobs I worked on, is say, okay, well, we had stainless. It's not a bad material. Yet what I want to do now is make sure I don't have the chlorides getting to the surface of the stainless. So you end up putting a coating on the stainless steel. But the idea there with the coating is not to protect against just moisture penetration. You just want to prevent the chlorides from getting to the surface. So it's easier. As long as you prevent the chlorides from hitting that surface of with the passive layer, then you can prevent corrosion. A lot of issues happen with stainless steels. This one here was just a little test to show that it was contaminated with regular steel, structural steel. So if I have a nice piece of stainless and I smear a little bit of regular steel on it, now all of a sudden, when it's exposed to the environment, it can be just a very small amount, but locally it's going to start the reaction because I'm taking away some of the protective layer and replacing it with just regular carbon steel. So you have your best material, then just handling tools, cranes, chains, you name it. If they contaminate your product, you end up with corrosion. This one just shows a little example of that pitting at the very small scale. When you have these holes, after you pitted for the first time, even if you clean up and you put the coating, what I found on a number of projects is you're still more likely to pit again because you created these sites, these holes that are likely to continue over and over again. Now, what exactly these sites look like, you can see a few of them here. So they're very similar to the holes I showed you on the copper pipe. It just really penetrates. It's almost like drilling. So even if you would go through a very rigorous process trying to get the chlorides out of that hole, it's still a hole, and next time it's exposed to a certain environment, it will try to continue working the crevice effect at that point, and then start to segregate the iron. So maybe the lesson with the stainless steel is they are not all with the same resistance to corrosion. So here you have different styles. I said what you were looking at was a 316, which is a good grade for just general use against corrosion. But if you're talking about an industrial application where you're going to have a lot of chlorides, then there are many more steps that you can go in the ability to resist the corrosion. Yes?
In the pics that you showed, is there complete loss of coating? I mean, there's absolutely no coating there whatsoever.
Yeah, it becomes a very active surface. It's the anode here where on the surface you're in direct contact with your electrolyte to become ionic. Yes.
Okay.
And that's why it goes pretty fast in that local zone. Now, if you end up with a buildup and then all of a sudden you plug that interface between the two, the reaction stops. And it does tend to happen when you reach a true thickness condition. So having a very, very small true hole is common. And then at that point, it's not as easy to get a cell effect. You're not confined in a hole, but you penetrate it all the way through and you have flow. So the conditions, local conditions are just really changing at that point. And you can protect again. One way you get into trouble with the stainless steel is locally here, you lose, when you have all these reactions, you lose the oxygen content. If you have the ability to bring more oxygen, then you can repassivate again. And that's what the flow of water will do to you, for example.
So then where does the chlorine go, the chloride go at?
I will have to stop so and I can continue with him, or I don't know who has class, but okay, go ahead.
What happens to the chlorides after that?
Hold on. So Tuesday, we have class at 9, and that's the last one, essentially. After that, it's starting the class presentations. Thank you. Good.